In this lecture, we're going to discuss the solvents that would be used in nuclear magnetic resonance, especially for hydrogen NMR or proton NMR. And we're also going to discuss what is meant by the term chemical shift, because previously we were using the term frequency. Very quickly, I'm going to give you a brief introduction of H-NMR very quickly. So you have the first thing that we discussed about H-NMR was that these hydrogen protons, they have a magnetic spin or magnetic spin moment, or you can say that they act as tiny magnets. So they have a north pole and a south pole, and they act as tiny magnets. And when you place them in an external magnetic field, so let's say this over here is your external magnetic field, then all these tiny magnets, these hydrogen protons, they're going to align with the external magnetic field. So they're going to start pointing in the direction of the external magnetic field, and this was called, this was known as a low energy state, because all the, or aligned spin, because all the hydrogen protons are aligned with the external magnetic field. Like a compass needle, the compass needle is always pointing in the north, pointing in is always pointing towards the north because the Earth's magnetic field is more dominant. Similarly, if this external magnetic field is going to turn all the hydrogen protons and align them with the external magnetic field, so they would all be pointing in the direction of this external magnetic field. But then what happens is that if you give radio waves to these hydrogen protons are going to absorb frequencies from these radio waves, and they're going to become energetic. If they become energetic, the energetic protons can go into opposing spin. They would have enough energy to go into opposing spin, and they can then oppose the external magnetic field. So this is called resonance. By gaining energy or absorbing a frequency from radio waves, these hydrogen protons can go into opposing spin. These hydrogen protons can also do exactly the same. They can go into opposing spin by gaining energy from radio waves, and they're going to absorb specific frequencies from these radio waves. Now, the energy needed for resonance depends on chemical environment, which is a very important factor. Chemical environment is that there are electrons that are surrounding the protons of this hydrogen. These electrons, for example, if they're bonded to oxygen, these electrons would be closer to oxygen, so the proton would be more exposed, and it's going to experience a greater amount of magnetic field. So it would be more difficult for that proton to go into opposing spin and point in the opposite direction. So it would need a higher amount of energy. If it needs a higher amount of energy, we know that energy is proportional. It's proportional to frequency. So if a higher amount of energy is needed, a different or a higher frequency would be absorbed by this particular proton. Similarly, if you look at these hydrogen protons, they're bonded to carbon, so the electron cloud would be very much present, and this electron cloud would shield the proton which is inside it. So there would be electrons around. Let's randomly draw these electrons. These electrons would be surrounding the hydrogen proton, and these electrons are going to protect that hydrogen proton from the magnetic field, from the external magnetic field. So this hydrogen proton is not going to experience a very large magnetic field, so it would be very easy for that proton to go into opposing spin. Not a lot of energy would be needed. So when it's absorbing energy, less energy would be absorbed and a lower frequency would be needed. So you have all these hydrogen protons, and they would be absorbing different frequencies. But if you look at these three hydrogens are very identical. They have exactly the same shielding. They have exactly the same chemical environment. They're all bonded to the same carbon atom, so the electron cover that is around them is going to be exactly the same. They're all bonded to the same carbon atom. So these three hydrogens, they would all be resonating at the same frequency, and let's call that frequency F1. Whereas this hydrogen over here is different from the other hydrogens. Shielding effect would be different. The electron cloud would probably be missing because of the highly electronegative oxygen, so the electrons would be closer to this oxygen. So the proton is going to be more exposed. It's going to experience a greater amount of magnetic field. So it would be more difficult for this hydrogen proton to go into opposing spin. So it would need a higher energy, or a different frequency would be absorbed, and let's call that frequency F2. So two different frequencies would be absorbed, F1 and F2. Three hydrogens would be resonating at F1, and one hydrogen would be resonating at F2. Let's draw and plot this now. So here over here is your NMR spectrum. Three hydrogens from this molecule over here, three hydrogens would be resonating at frequency F1. So they would be absorbing frequency F1. So this is the absorption shown of frequency F1. And one hydrogen would be resonating or absorbing frequency F2. It has a different chemical environment. It absorbs a different amount of frequency. A different frequency F2 would be absorbed. So a frequency F2 would be absorbed. The frequency absorption, the height, the relative height of the absorption, since three hydrogens are absorbing F1, F1 would be absorbed three times more compared to F2. So the ratio of the peaks would give you an idea about the number of hydrogens in different chemical environments. So three hydrogens, if you look at this molecule, three hydrogens would be absorbing frequency F1. So the absorption of F1 would be greater, three times greater compared to the absorption of F2 because only one hydrogen is absorbing frequency F2. So this is how the NMR spectrum would look like. Now, what we are now going to discuss now is NMR spectrums are not given, this axis is not given in terms of frequency, but it's given in terms of chemical shift. And we're going to determine or discuss what is chemical shift. We're going to move towards discussing what solvents are used when NMR spectroscopy is done. So here I have my propanol molecule and it's placed in an external magnetic field. This propanol molecule has all these hydrogen protons having magnetic fields and they would all line up with the external magnetic field. So these three hydrogens are in the same chemical environment. They have the same shielding. They would resonate at frequency, let's call that F1. Then you have these two hydrogens in exactly the same chemical environment. And these two hydrogens would resonate at frequency, let's call that frequency F2. Then I have these two other hydrogens and they have exactly the same chemical environment, which is going to be different from these two hydrogen atoms because the shielding would be different. This carbon is bonded to a single oxygen, so the shielding of these two hydrogens would be slightly different from these compared to these two hydrogens. So these two hydrogens are in the same chemical environment. So these two hydrogens are going to resonate at frequency, let's call that F3. And then I have this hydrogen at the end. And let's call this, that this hydrogen resonates at frequency F4. So I have four different chemical environments of these hydrogen protons. They're resonating. Initially, they would be aligned with the external magnetic field. And if they gain energy from radio waves by absorbing these particular frequencies, then they would go into opposing spin and they would start opposing the external magnetic field. The energetic hydrogen protons are going to be able to oppose the external magnetic field. So this is what resonance is. Now I'm going to talk about the solvent that is used in when you're doing NMR spectroscopy. So for example, I have this propanol molecule. This propanol molecule, and now I'm going to add a solvent because this propanol molecule would be mixed in a solvent that would be present with this propanol molecule. So let's assume for a second that the solvent is water molecules. Now the problem with using water as a solvent is that water has its own hydrogen protons which would be aligned with the external magnetic field, and if they gain radio waves, frequency from radio waves, they become energetic. They would go into opposing spin and they would reach this energetic state by absorbing radio frequencies. So the problem with adding water is that it has its own resonant frequency. So H protons in H2O will resonate and they would cause confusion because you would not be, it would become very confusing. You would not be able to know whether the hydrogens in this propanol molecule, are they resonating or the absorption is because of the solvent that is being used. So the issue now is you're going to use a solvent that does not cause resonance. Or if it resonates, its resonant frequencies are going to be very different from the resonant frequency of these protons, so there is no confusion. You would be able to easily differentiate whether the frequencies that are being absorbed are from the protons in the molecule or from the solvent that is being used. So for example, water is probably going to be a very bad solvent because the hydrogen proton in H2O would have almost the same shielding as this OH proton. So this resonant frequency and the resonant frequency of these protons in H2O, they would be very, very similar. So that would cause a lot of confusion. So you're not going to use water. Water would be a pretty bad solvent. Instead, one very popular solvent is deuterated chloroform, which is CdCl3. The first property of this deuterated chloroform is that it has a wide variety of dissolving. It has the ability to dissolve almost any organic solvent. So a lot of organic compounds are going to dissolve in deuterated chloroform. So when you take a solution with this particular molecule in it and you're trying to do NMR spectroscopy, this molecule is probably going to dissolve in CdCl3. The other very important thing about this molecule of deuterated chloroform is that there is a deuterium isotope used instead of the hydrogen isotope. So instead of using hydrogen isotope, you're using deuterium. Deuterium has one neutron. Both are isotopes of each other. They're both deuterium is an isotope of hydrogen. Hydrogen just has one proton in its nucleus. Whereas on the other hand, deuterium has one proton plus one neutron. So it's an isotope having one more neutron. The only difference between the two atoms is this extra neutron in deuterium. Now, what that would do is that the nucleons are going to be paired now. They're going to have paired spins. One would be pointing in one direction, the other would be pointing in the opposite direction. So you would have two nucleons, which would result in the cancellation of the magnetic spin. There would be no net magnetic spin, no net magnetic spin moment or dipole would be created. So deuterium would inherently be non-magnetic. It would not act as a tiny magnet. So deuterium is not going to resonate. Hydrogen protons are capable of resonance, but deuterium would not be capable of resonance. So there's not going to be any interference. These CdCl3 molecules, their deuterium atoms, they're not going to resonate, which means that the only thing resonating in your solution would be the hydrogen protons that are present in this molecule over here. There would be no interference in the nuclear magnetic resonance spectroscopy because of the deuterium atoms in CdCl3. So CdCl3 is going to be a very good solvent. It would not cause any interference. It would not cause any confusion. If you see hydrogen protons resonating, you would be pretty certain that they would be coming from these hydrogen protons. Nothing from this would be resonating in the solution itself. The other thing that we are going to discuss now is the term chemical shift and tetramethylsilane, which is known as TMS. I'm going to quickly first discuss the NMR spectrum of this molecule over here, methanol. And as you can see, you have these hydrogen protons, and these hydrogen protons are going to resonate. These three hydrogen protons have exactly the same chemical environment, so they would resonate at exactly the same frequency. So let's say that these three hydrogens are resonating at frequency F1. So they have exactly the same shielding, they're exactly the equivalent type of hydrogen, they have exactly the same environment. So initially they would be aligned with the external magnetic field, and if they absorb this particular frequency from radio waves, they're going to go into opposing spin. They would start, they will become energetic, and they would be able to oppose the external magnetic field, and they're going to gain energy using this frequency F1. So I've drawn a table of the NMR spectroscopy. So frequency F1 would be absorbed by three hydrogens. So the absorption of frequency F1 is going to be 3 times more compared to the absorption of this hydrogen over here. This hydrogen has a different chemical environment. Its shielding is different. It experiences a different external magnetic field. So initially this hydrogen proton would be aligned with the external magnetic field, and if it gains energy by absorbing frequency, let's call that frequency F2. So if it absorbs frequency F2, the energetic proton would then start going in the opposing spin, or would start opposing the external magnetic field because it's now energetic. So you have this hydrogen proton, because of its different shielding, different frequency would be absorbed for resonance. But there's only one hydrogen, and let's call that frequency F2, which is going to be absorbed. But since there's only one hydrogen, so the absorption of frequency F2 is going to be lesser compared to the absorption of frequency F1. So three hydrogens resonating at frequency F1, and only one hydrogen resonating at frequency F2. But now there's an issue. The issue is that the NMR spectroscopy, this x-axis over here, is not given by frequencies, but it's given in terms of chemical shift. For example, you're not going to see frequency F1, but instead you will be given delta shift would be given, delta parts per million. So these three hydrogens would be written as that they are resonating at 3.35 parts per million, whereas this one hydrogen over here is resonating at delta 5.5 parts per million. Now the frequency and this delta shift, they're pretty much the same, except for the fact that when you're talking about delta shift, you're basically talking about the frequency of those hydrogens in comparison with the standard, which is TMS. So all these hydrogen protons, so you don't talk about frequency in absolute terms. You don't mention about the frequency at which these hydrogens are resonating. But what you talk about is it's the frequency shift, or the difference when you compare it with this standard TMS. So all the hydrogen protons, their frequencies would be compared with this TMS. So we need to understand how is that comparison done. So the first thing is, just clarify this in mind, that the term frequency and this delta shift, they're pretty much proportional. I mean, there's no difference. You're using frequency frequencies would be absorbed, but those frequencies would always be commented in relation to this standard. So instead of using the term frequency on this axis, you would be talking about the term delta shift. So let's first find out what do we understand by the term delta shift. So the first thing is, here's by tetramethylsilane or TMS. This is known as TMS. So this is the TMS molecule. The first thing you would notice about this TMS molecule is that all the hydrogen, this is my standard, all the frequencies of hydrogen protons, all the hydrogen protons and the resonant frequencies are going to be compared with the TMS frequency. The first thing you would notice is that all the hydrogens are equivalent. So all H protons are equivalent and they're going to resonate at exactly the same frequency. So 12 hydrogens are going to resonate at exactly the same frequency. They're going to absorb the same frequency. Initially, they will be aligned with the external magnetic field, and when they gain energy, they absorb a particular frequency. Let's call that F1 or let's call that F0. This would be our standard frequency. All the frequencies of the other hydrogen protons and other molecules, they're going to be compared with this frequency of TMS. So let's assume that this F0 is getting absorbed, this frequency is getting absorbed, and they would all start resonating. They become energetic and they start going in the opposing spin. All the protons, they start going in the opposite or opposing spin, and they're going to absorb frequency F0. So this is going to be the TMS peak. Frequency F0 is going to be absorbed. One other thing about TMS protons is that TMS has the most shielded hydrogen protons compared to all the other organic compounds. So they have a lot of electrons. The protons, the nucleus is surrounded by electrons or shielded by electrons. So it doesn't experience a lot of external magnetic field. So it needs the lowest frequency, it needs the least amount of energy for resonance or go into opposing spin, because the hydrogen protons are shielded by electrons. So it's not going to experience a lot of magnetic field. The external magnetic field would be deflected off of those electrons that are surrounding it. So there would be lots of electrons that would be surrounding this, protecting the nucleus. So it needs the lowest amount of frequency for resonance. So compared to the other protons, so it would be very distinguishable. It would be on one side of the frequency spectrum or one end of the frequency spectrum. The lowest frequency would be needed for resonance for TMS. So coming back to our point, what does delta shift means? All the frequencies of all the other hydrogen protons of the other molecules. For example, I have a molecule of methane. The hydrogens in methane are going to resonate. So you're going to compare the frequency resonant frequency of these hydrogen protons compared to the frequency of the hydrogen protons in TMS. So a delta shift would be always written by the symbol delta. A delta shift of 10 basically means that a particular compound needs a radio frequency 10 millionths more than that of TMS. So delta shift indicates how much more frequency, how much stronger frequency would be needed for resonating these protons compared to the protons in TMS. So in simple terms, let's compare these hydrogen protons. Let's assume they're resonating at frequency F1. So these hydrogen protons are resonating at frequency F1. TMS resonates at frequency F0. So delta shift is simply what's the difference between these two frequencies. How much stronger is F1 compared to the TMS resonant frequency? So a delta shift of 10 basically means that a particular compound needs a radio frequency 10 millionths more than that of TMS. So your delta shift would depend on the difference between the TMS frequency, these hydrogen protons resonating, and the frequency of your protons in your molecule. What's the difference between these two frequencies? So that would indicate what delta shift is. So I'm going to now discuss a table that is given to you in your exams. So let's open that table now. So here is the table that would be given to you. It's a typical H-NMR chemical shift values relative to TMS as they have written. So everything would be compared. All the resonant frequencies are going to be compared with how different they are from the TMS peak. The TMS is 9, chemical shift 0. So everything is being compared by the resonance of TMS. So as you can see over here, the first thing is you have protons bonded to carbon. So CH protons, any proton that's bonded to carbon, so it could be protons in alkane, they would resonate at a chemical shift of 0.9 to 1.7 delta shift. Then you have an alkyl, carbon protons bonded to carbon which are next to C double bond O. So if protons are next to C double bond O, they would resonate at 2.2 to 3. They would have a different amount of shielding. So the resonant frequency is going to be different compared to TMS. Then you have protons next to an aromatic benzene ring. So if there are protons, a carbon chain, an alkyl chain next to aromatic benzene ring, they will resonate at 2.2 to 3. And you have all these different combinations. So basically, you have all these hydrogen protons and the different environments, and the chemical shifts are provided in this table. You can see, for example, over here, hydrogen could be bonded to oxygen as well. So it could be part of an alcohol, it could be part of phenol, it could be part of carboxylic acid. It could be then hydrogen could be bonded to nitrogen, so it could be part of amine, phenylamine, amides. All of them would have different shielding. They would have different chemical shifts. So what I'm going to do now is I'm going to try and construct an NMR spectrum based on the chemical shift table that is given over here, that is provided over here. So the first molecule that I'm going to draw the NMR spectrum would be for propanoic acid. This over here is a propanoic acid molecule, and you have 1, 2, 3, 4, 5, and 6 hydrogen protons that are going to resonate. These 3 hydrogen protons are equivalent. They're going to resonate at exactly the same frequency. Then these 2 hydrogen protons are going to have exactly the same chemical environment. They're bonded to the same carbon atom and with the same groups around them. So they are equivalent and they would resonate at a different frequency. And then you have this hydrogen over here that is going to have a different chemical environment. So let's now go and refer to the table. I'm going to first figure out where would these 3 hydrogen protons resonate. Remember this, these 3 hydrogen protons are bonded to a carbon atom, which is part of a carbon chain. So hydrogen protons bonded to a carbon chain, part of a carbon chain. What chemical shift would they resonate at? So over here you can see the hydrogens that are bonded to carbon, and we have this alkane type, this carbon chain hydrogens. They're going to resonate at around 0.9 to 1.7 chemical shift. So these 3 hydrogens are resonating at 0.9 to 1.7 chemical shift according to the data booklet. Let's focus on these 2 hydrogens now. These 2 hydrogens are bonded to a carbon, which is bonded to a carbon with a double bond oxygen. So their shielding is going to be different. So let's look at the data booklet again. So over here, you're going to notice that carbon with hydrogens bonded to a C double bond O. That's given over here. This is the closest resembling hydrogen protons to the ones that are given in our molecule. And they resonate around 2.2 to 3. So their chemical shift is around 2.2 to 3. Remember, their range is given. Molecules are not always exactly the same. So every molecule is going to have slightly different chemical shifts. So when you're talking about chemical shifts, there's always a range given. 2 molecules are never identical. So around 2.2 to 3 are these hydrogens next to C double bond O. So that's the chemical shift for these 2 hydrogens. And then let's look at this hydrogen over here, which is going to be very different from the other 2 hydrogens. They were pretty similar. The chemical shifts were very close together. But this one is going to have a completely different shielding because it's bonded to oxygen, which is very electronegative. So the electron cloud around this would be very different compared to the other hydrogen protons. So different shielding. So it's a hydrogen in the carboxylic acid group. So over here you can see this is the hydrogen protons bonded to oxygen. We're not going to talk about this one. This is alcohol, this is phenol. We're talking about this proton over here, this hydrogen proton, which is part of the carboxylic acid group, and it's resonating at around 9 to 13. So it's very different from the other hydrogen protons that we discussed. So here's this hydrogen proton resonating at chemical shift 9 to 13. That's the range of this hydrogen proton. So this over here is the actual NMR spectrum with the chemical shift values. Remember, the height of the absorption tells you the number of hydrogen protons in that particular chemical environment. So there's one resonance in this range 0.9 to 1.7, which is given over here. So the height is relative height is 3 because you have 3 hydrogen protons. So this frequency would be absorbed 3 times more compared to the other frequencies, or the ratio of the peaks, or the height of the peaks, or the height of the absorption would be 3:2:1. This would be the least absorbed because there's only 1 hydrogen proton in this environment. So 1 proton resonating at 9 to 13. So there's an absorption at 12, and there's the 2 hydrogen protons resonating at this 2.2 to 3 range. So it's given over here. So this is the NMR spectrum of propanoic acid. Let's try and do this other molecule, which is 2,2-dimethyl propanoic acid. So 2 methyl groups attached on the second carbon atom of propanoic acid. Let's try and do the NMR spectrum for this molecule. So the first thing that you would notice is that you have these 3 methyl groups. I'm grouping them together. These three methyl groups have exactly the same environment for their hydrogen protons. These hydrogen protons are bonded to carbon, which is bonded to the same carbon atom. These hydrogen protons are also bonded to a carbon atom, which is bonded to the same carbon atom. And these three hydrogen protons are also bonded to a carbon atom, which is bonded to the same carbon atom. So they have exactly the same chemical environment. So same chemical environment, and so they're going to resonate at exactly the same frequency or chemical shift. Now we're going to look at the chemical shift of these hydrogen protons. Now this is the alkane type, because these carbon atoms, these hydrogen protons are bonded to a carbon chain only. So if you look at the table over here, these hydrogen protons, alkane type on the carbon chain, it's 0.9 to 1.7 chemical shift. So this is the range of these, the resonant frequency. So you have almost 9 hydrogens actually resonating at exactly the same chemical shift, 0.9 to 1.7. So you have 9 hydrogen protons resonating at exactly the same chemical environment. And then there's this hydrogen over here. This hydrogen is going to be different from the other hydrogen because it's bonded to oxygen. So this hydrogen, the first thing is, let's look at the chemical shift. It's part of the carboxylic acid group. So let's look at the table. And you would notice that in the table, you would notice this hydrogen proton next to oxygen. It's part of the carboxylic acid group. So its chemical shift would be around 9 to 13. So it's going to resonate at around 9 to 13 chemical shift. The chemical shift is 9 to 13. So here I've drawn the NMR spectrum. You're going to notice a chemical shift, resonance of 9 hydrogen protons at around, it's given at 1.1 parts per million, so it's within that range. And then there's one hydrogen resonating at, for this hydrogen over here, that's resonating at 10.1 parts per million. So you're only going to get 2 peaks. These 9 hydrogens are in the same chemical environment, whereas this hydrogen is in a different chemical environment.